Thanks ACS for giving young researchers the opportunity to share our work in a more visual way. I'm going to highlight the most important results obtained during the development of a new heterogeneous catalyst to perform the hydrodeoxygenation of N-Heteroaromatic compounds to the corresponding Azaisoindolinones. These kind of compounds are considered privileged scaffolds in medicinal chemistry because its derivatives are biologically active against several disorders such as Alzheimer's or autoimmune disorders. However, the main part of the work to perform the hydrodeoxygenation of cyclic imides uses phthalimides as starting materials, because in this case both carbonyl bonds are chemically equivalent. The presence of a pyridine ring in phthalimides makes it an additional selectivity challenge because it can be hydrogenated and also both carbonyl bonds are chemically different. In fact, if you want to perform the reduction of phthalimide to Azaisoindolinones, there are only two protocols, and they suffer important drawbacks, such as the generation of great amount of waste and the lack of applicability that limits its applicability from a sustainability point of view. In this context, in our group, we report the first heterogeneous catalyst to perform the hydrodeoxygenation of cyclic phthalimides to obtain Azaisoindolinones generating water as the only reaction byproduct. The material is based on silver and rhenium aggregates onto the alumina surface and can catalyze the reaction of more than 20 cyclic phthalimides, tolerating the pyridine ring. In this slide, I show you the most important examples for the reaction scope, and it can tolerate the presence of electron-donating groups and also electron withdrawing, as well as heterocycles. And I want to highlight compound 16, in which the presence of aryl bromide can allow us to obtain more functionalized compounds, and compound 25 that has the pyridine ring that is present in biologically active compounds. Finally, we propose a reaction mechanism based on previous estimation. The initial material is formed by silver perrhenate aggregates, in which in the medium it can generate the active material that is constituted by silver nanoparticles and rhenium oxide clusters from different oxidation states. The first hydrogenation of the carbonyl bond is assisted by the Lewis acidity of several species, such as the aluminum surface and also the high-valent rhenium oxide species, to generate the hemiamidal 3. Finally, the hydrodeoxygenation of the carbonyl oxygen bond can be done in two different ways. In both of them are assisted by the Lewis acidity of the rhenium oxide clusters. But in one case, the silver nanoparticles can promote the hydrogenation, and in the other is the low-valent rhenium species, to generate the desired asalactam 2 and water as byproduct. In both steps, the regioselectivity of the reaction can be explained by the coordination of the pyridine ring to the Lewis acidity species of the catalyst. Finally, I would like to thank my PhD supervisor, Rosa and José Ramón, and also my colleagues, Luis Izquierdo and Camilo Arango. I shared the co-authorship with Luis, and also two master students, Patricia, Camilla, and Pau. The work was performed at the Instituto de Tecnología Química at the Polytechnical University de Valencia and also at the University de Valencia. Thank you very much.